to have here today Igor Di Marco. Let me just a brief introduction about Igor. Igor received his PhD in 2009 from Radboud University in Nijmegen in the Netherlands. And then from 2009 to 2017, he has worked at the Uppsala University in Sweden, first as a postdoctoral fellow and then as a staff scientist. In 2017, he became a junior research group leader at the Asia Pacific Center for Theoretical Physics in Pohang in South Korea. Igor has authored about 70 scientific articles in several prestigious journals, including Science, Nature Communication, and PRL. And so he has obtained research grants from the Swedish Research Council, the Carl Truggers Foundation, and the National Research Foundation of Korea. And his research interests, which we'll see now during this talk, are focused on understanding systems with strongly correlated electrons, and in general, developing computational tools to describe them. His most important works contributed to the understanding of transition metal elements, strongly correlated oxides, and dilute magnetic semiconductors and rare earth compounds. Well, I would say most probably you guys are here to listen to Igor and not to me. So again, I thank Igor for being here, and I look forward to his talk.
Okay, thank you very much, Marco, for the nice introduction. So today I intend to discuss some my work on the study of strong electronic correlations in materials. And this will be done by a method called dynamical mean field theory. And I will cover several studies, try to investigate, to show you all different regimes of correlation. So from the transition metals, plane elements, up to rare earth compounds. So as Marco showed you, I am actually working mainly in, as Marco mentioned, I'm working mainly in South Korea, in Pohang, where I lead a group at the Asia Pacific Center for Theoretical Physics. And I'm still affiliated to my old institution in Sweden. So it's two very different and extreme environments. So this is an overview of the people that have contributed to the material presented to this in this talk and to my research in general, in particularly my group at APCTP, and also my former group at Uppsala University, led by Professor Ole Eriksson, plus other theoretical collaborators and experimental collaborators. Okay, so I will start presenting a very basic overview of the concepts we are going to discuss today, and then I will focus more on more complicated things. So in condensed matter physics, in general, we are lucky because we know already what the rules of the game are. We know that we have simply to solve the Schrödinger equation of electrons and nuclei. Now, this is something we can do for an atom because the number of degrees of freedom are in fact limited. And we can solve this by a variety of techniques nowadays. And we obtain a set of discrete energy levels, each corresponding to a given electronic configuration. I assume that all students here are familiar with this. And this is the shell model is what brings to the formation of the periodic table. In a solid, things get a bit more complicated because in a solid, now we are considering, let's say, we would like to model a macroscopic sample of matter. And so the number of constituents is much larger, of the order of the Avogadro number. This means that solving the problem exactly is not possible. So we have to revert to some approximation. A very simple approximation one can do is the one particle approximation. And this is what's done when one formulates the band theory. And in the band theory, in fact, we can establish that the electron in a solid, they do not like to have this localized behavior any longer, but they would prefer to have an itinerant behavior, so delocalizing the whole crystal. And instead of forming discrete energy levels, they now form continuous energy bands. But then we can ask, how adequate is this simple picture? As a matter of fact, it is very adequate, and this is also a posteriori justified by the great success of density functional theory. Density functional theory is the most successful computational theory we have out there, and nowadays many studies in condensed matter, they are based on it, or they have density functional theory as a computational support. It is the idea of density functional theory is very simple. It actually relies on two pillars. So first of all, the focus is shifted from the wave function of the many electron system that contains a very large number of degrees of freedom, one for each electron, or 3 for each electron, if you prefer, 4 if we include the spin, to the electron density n of r, which has only 3 degrees of freedom. So it's a huge simplification. And then the second pillar in the Constant formulation, in density functional theory, we are actually solving the system of interacting electrons, mapping it onto a system of non-interacting electrons moving in an effective potential. The advantage of this mapping is that now we can solve the system that I'm showing you on the right. So, and then we can formulate a set consistency condition so that we can also give a good solution of the original problem. The key advantage of all this technique is that in this way, we do not need to simplify our original Hamiltonian. We can work directly with it. And this is a very good thing, because it means that all our calculations, all our theories are in fact material specific, because we work directly with the full Hamiltonian. And this generality allows, in fact, to predict a huge number of properties, from the equilibrium crystal structures and elastic properties, magnetic properties, optical properties, really a lot of things, and also for a huge number of systems. So from molecules and solids and non-dimensional systems, impurities. And the success is based on the high accuracy and the high computational efficiency. But then we can ask ourselves, is this approximation suitable for all systems? As a matter of fact, it's suitable for most systems, but not for all of them. Some electrons, like those associated to unfilled, to partially filled 3D shell, like from vanadium to copper, and 4F and 5F shell, so in the lanthanides and in the actinides, in these materials, things may not be so simple. So what does it go wrong with localization? We can see it in this scheme. On the right side, I'm showing you what happens in density functional theory. We have that each electron sees the presence of all the other electrons around it as a time average electron density. So then an electron will move in this average potential. However, if the localization of the electron we want to discuss is strong, then we have to keep in mind that the electrons are charged particles, so they will experience a strong Coulomb repulsion. So if their particle nature emerges, then when they meet in a solid, they will like to repel each other. Now we understand, and this kind of picture is also very difficult to describe in this language that you see on the right. And because now the behavior of each electron is correlated to the behavior of the other one, we talk of this material as strongly correlated systems or materials. So therefore, we have now defined the problem that we want to discuss today, the problem of strongly correlated materials. So we can tell this as a tale of undecided particles. So these are electrons that are still undecided if being very localized, like in an atom, or very delocalized, like in a one-particle approximation of solids. And in reality, in all material, these two characters, they will coexist. But in some of materials, one of the characters will emerge, in some other materials, another one, and most material will be intermediate. For example, and this is a very active branch of studies in physics. Actually, many interesting physical phenomena are related to these strongly correlated systems, like superconductivity, condophysics, really a lot of very exciting and exotic also phenomena. And one that I will discuss is briefly is the mode transition. This may happen, for example, in 3D oxides when the 3D electrons are very localized. Then in this case, the strong correlation effects may lead to a dramatic difference with what band theory would predict. Let's focus, for example, on the electron that we have now here in the top left side of this crystal. If this electron tries to move to the neighboring side, we will see that as soon as we reach the close ion, it will actually encounter another electron, and therefore will experience strong Coulombic repulsion that will bounce him back. We understand that in this picture, each electron is bound to his own ion because they cannot move, because they are constrained by this strong Coulomb interaction. So basically, we transform the whole system in a big traffic jam. And this is a pictorial view of a Mott insulator. Okay, then we can ask, are there theories out there that can describe this strongly correlated system, that can describe the Mott transition or the Kondo physics? There are a few of them. Each of them has its niche of applicability. The one I'm specialized in is called the dynamical mean field theory. Dynamical mean field theory can be explained in very simple terms, in fact. Let's consider a crystal that we want to describe quantum mechanically. Now, what we do in dynamical mean field theory is that we map the atomic problem of one atom in the crystal onto a problem of one atom embedded in a self-consistent electronic bulk. Now, as you can see, this idea is very similar to what I presented when I presented DFT, because they are all, these kind of formulas, they can be all categorized into the same family of theory. The difference is that here, the quantity we map from and we map onto are different. And the advantage here is that the system we are mapping onto is a system where the electrons are still interacting. So here they are not non-interacting electrons, they are still fully interacting. And this system is called an effective impurity model. The advantage of this effective impurity model is that, differently than the system we use for DFT, for plain DFT, is that it is still a fully dynamical quantum object. This means that the quantum fluctuations that you can see on the right, where electrons jump back and forth from the bath to the impurity, are in fact properly described, exactly described. The approximation in this case is due to the fact that we are considering only one atom in an effective medium. So then the problem becomes naturally local. This means that the spatial fluctuations are in fact frozen. So it's still a fully dynamical quantum object, but most importantly, it's an object that we can solve. So this is a problem that is solvable in many-body theory. And there are many techniques to solve. Some of the ones that I will use in my presentation, they include the Ab-1 approximation, exact diagonalization, or this SPDF approach, or even the R3-FOC, you can solve it, and then you get the DFT+U method. Okay, so DMFT in general is can be formulated for model, and there's a very clear and straightforward implementation. But most importantly, it can also be combined with DFT. And in this case, you get to the DFT+DMFT scheme, which tries to merge the accuracy of DMFT for describing strong correlation effects with the generality of DFT to provide a material-dependent framework. So the implementation I will use in my discussion of my results is my own implementation, implemented into the RSPT code that I am one of the developers of. And it is an all-electron, full potential, linear muffin-tin orbital code. In our recent assessment of DFT codes, it has been shown to be one of the most accurate codes that you can find. And it is our DMFT implementation. It is fully general and also rather computationally efficient due to the fact that the LMTO basis is in fact very small. Okay, so here I close the methodological part of my talk, where I wanted to discuss the method and in the context where I am going to use it. Now I will focus more on material applications. In this analysis, I will follow I will follow this order showed in this scheme, where I will analyze materials for different degrees of localization. So I will start discussing the transition metal elements, and then I will focus on transition metal monoxides. And finally, I will go to the limit of localized electron behavior that corresponds to the rare earth elements and compounds. So, okay, so from here, I also want to mention something that also Marco mentioned at the beginning. So if you have questions, please interrupt me and I will do my best to reply. So we start with the discussion of the correlation effects in iron, cobalt, and nickel. Now, iron, cobalt, and nickel are a bit of intermediate material, because if we go back, and you can see here in the scheme, they are very close to the applicability limit of DFT. In fact, plain iron, cobalt, nickel, and manganese, they can be studied also with DFT. DFT is very good for them. And it's just when you go to the more subtle features that it becomes important to account of the role of correlation effects. For example, DFT for the magnetism of iron works pretty well. I mean, in fact, it can describe many properties of iron. But when we go and look at the photoemission spectrum, for example, then the discrepancies arise. So for the students, a brief reminder of what is photoemission. In photoemission, we are shining a sample with light, and then the photons that hit the sample, they excite electrons from the occupied valence band to the continuum. And these electrons, they can propagate then and escape out of the surface, and then they can be revealed, they can be measured with a detector. And by changing the angle that you see here, the angle of the detector, then we can retrieve very accurate information on the band structure. And of course, on the density of states, if you integrate it. So, and I will call of these techniques as ARPES and PES. So in ARPES and photoemission, we see, in fact, two major signatures of strong correlations. We see a decrease of the 3D bandwidth with respect to what DFT predicts. And we see also the formation of high energy non-coherent satellites. I was involved in this in a series of work in collaboration with Bessie in Berlin, with experimental scientist Bessie. And we aim at clarify to what extent really these correlation effects are important and to what extent DMFT corrects them. And these are a bit of not very recent studies, but they are important because they help put things in context, especially our discussion on the magnetism that will follow. So we identify that these materials are well described by DFT+DMFT. We also identify that the agreement worsens from nickel to iron. The reason why it worsens, in fact, is something that we can explain. And we identify that there are effects that are beyond the DMFT. And this is also supported by other experimental evidence on the measurement of the effective mass at the Fermi surface in iron. And this, of course, this point on the effect beyond the DMFT, it becomes important in the moment where, you know, we want to make our theory more and more accurate. So we always would like to push the boundary of the accuracy of what we are doing further and further. But let's have a look a bit of what's happened. This is an example of the reduction of the 3D bandwidth. This is, you can see on the left side, the photoemission spectrum that corresponds to this thick line as a function of the binding energy. This is the intensity on the y-axis. As you can see, there are two major peaks close to the Fermi level, plus another peak at around 2 eV. Now, this peak is very broadened due to the lifetime effects that I will treat in a second. But it is there, you can observe, you can also observe how it moves. This is for data at the gamma point. And what we observe when we compare with DFT, we observe that corresponds to this dotted line. We can see that the DFT, in fact, gives a much wider bandwidth. So we can see that this peak is very off with respect to this peak here. In fact, this is a correlation effect, and we can observe this in DMFT when we change a little bit the degree of the strength of our local electron interaction, which can be tuned in DMFT if you wish, or can be calculated to represent the material. But here we tune it just to observe this effect that the more we increase our U, the more our bandwidth becomes narrower. And we can see, in fact, that when we increase U substantially, then we get an agreement of these two peaks, very much in line with the experiment. We can, of course, make the same comparison directly for the band structure. So here, what I report are the DMFT and the DFT, with this LSDA, spectral functions, and the experimental peak positions are reported by these points that you see in the plots. On the left side, I'm reporting majority spin up, and on the right side, minority spin down. What we can see, in fact, we can see it also here that the peak positions are the experimental peak position. They give a much narrower bandwidth than this is for HCP Cobalt than what we obtain in DFT. And in DFT, instead, we describe that narrowing much better. We can actually see from this picture another thing. In DFT, all the bands we are looking at, they are well defined, so you can follow the bands here in all ranges. But as soon as we go to the DMFT side, especially we can see it for majority spin, the band structure is destroyed as soon as the energy, the binding energy increases. And this is consistent with the Landau Fermi liquid theory that predicts that the quasi-particles, the excitations, they will acquire a finite lifetime as soon as you go far from the Fermi energy. And this is exactly what we see here. Close to the Fermi energy, we can still identify a band, but as soon as we go to higher energy, the bands get so broad that it doesn't make sense to speak of bands any longer. And this is actually something that we can make a detailed comparison with experiment, because we can use the experimental data now to fit the curves with a certain function, with Lorentzian functions, and measure, you know, these lifetimes. And this is something that you can see here, this comparison with the experimental points, with the error bars, and with the DMFT prediction. The two curves are for different implementations of the theory. And we can see that both for spin up and spin down, we get a rather good agreement. And this has been replicated, these results that we did in our study, also by other studies independent from us. Another thing we can observe is the formation of high energy non-coherent satellites. This is very famous effect, 6 eV satellite in nickel. We observe it in experiment here at about 6.3 electron volt. And we also observed that in experiment, the satellite is found to have a substantial majority spin polarization. And we reproduce this level with a reasonable accuracy also in the DMFT. We get it at slightly higher energy, the satellite, but it is there. And we also get the majority spin character to be dominating. Now, the discussion on the correlation effects can also be carried on to the magnetism subject, which is very interesting for iron because it's one of the most stable magnetic materials. Most robust, we can say, that is more correct. For the discussion of the magnetism, I would like to introduce another quantity, which is the inter-atomic exchange interaction. Now, what we can do, we can take our electronic structure theory and perform a mapping of the magnetic excitation onto an effective Heisenberg model. And this allows us, via this mapping, to determine this JIJ, this magnetic coupling. This JIJ in our formulas can be obtained as a response of to an infinitesimal rotation of two magnetic moments, one at atom I and one at atom J. So it really describes the coupling in between two moments in the solid. So here you can see an example of what's happened when you do this competition, this analysis of the magnetism for iron. These are the interatomic exchange coupling as a function of the interatomic distance in BCC iron. We can see that DFT, the blue curves, brings this behavior. We have a strong coupling for the nearest neighbor, and then the coupling slowly goes to 0. But as we can, slowly goes to 0, decays very fast. In DMFT, we can actually see a similar behavior. The coupling is a bit quenched for the first two neighbors, but then the agreement with the DFT is reasonably very similar results. In DFT+U, which is another method that is used often to analyze correlation, instead, the behavior is much more extreme. Now you get that there is a very strong quenching of the coupling between in the second neighbor with the second nearest neighbor. And this is unphysical. This is not what happens in iron. And the reason is that DFT+U should never be used to study metals. We can also analyze the long range oscillation, which have an RKKY nature that I will show you in a while. And what we can see is that, we can see that the oscillatory behavior is very clear if we scale the interaction to take into account of this damping. So if we multiply them with a factor, then we can observe this well-defined oscillation. More interesting feature, in fact, can be obtained by performing a symmetry decomposition of the exchange coupling. So if here we perform a calculation of the first neighbor, J1, exchange coupling from chromium to nickel. Let's look first at the total contribution that are given by these circles, open circles. We see that we have a contribution that increases from being anti-ferromagnetic to becoming ferromagnetic. Now, manganese in principle is anti-ferromagnetic, but here is ferromagnetic because we are constraining all this crystal structure to be BCC to allow for a better comparison without including the structural effects. So this is in agreement with what is predicted by the Bethe-Slater curve that defines how the filling of the 3D band should affect the magnetism. But when we make a symmetry decomposition in EG and T2G contribution, we observe something very interesting here. We observe, in fact, that there is that iron is the strongest antiferromagnetic component in the T2G channel. This is very interesting because iron is really the most robust example of a ferromagnetic material. So it's very surprising that we have such a strong antiferromagnetic component. It is the largest of all among all the materials we investigate. So this is very surprising. If we perform an analysis of the short-term contribution and we focus on the angle, what we can see, in fact, from the analysis, from the analysis of the angle, what do I mean the analysis of the angle? I mean that when we calculate the magnetic coupling, instead of doing a variation that is from like this, from parallel magnetic moments, I can do it like this, for the moments that are already partially bent. So, and we see actually that the T2G and the EG shell, they divide in a very drastic way. So the T2G component has no dependence on the angle, which means that our system has a purely Heisenberg nature. And instead, the EG components, they are very strongly dependent on the angle, which also means which instead means that there are strong non-Heisenberg components to this magnetism. To understand better this, we have to start looking at the density of states of iron more in detail. You can see it here plotted on the right. So as you can see, if we divide EG and T2G state, for here you have majority spin in the up and minority spin in the down panel, we can see that the conducting character of iron is defined uniquely by T2G electrons. It means that basically the EG electrons, they will be very localized, they will acquire a strongly correlated nature, but they will not define very much the conduction. Instead, the T2G electron, they will have a much more delocalized, regular itinerant nature. Now, if this is true, we could expect that the RKKY oscillations that we observed in the long-range behavior should have mainly a T2G character. And in fact, if we plot them, we observe exactly this. As you can see, there is a total quenching of the EG character, but the T2G character still defines these RKKY oscillations. And it's interesting, in fact, that now we can extract the fine detail of the Fermi surface and define certain vectors that are called Caliper Vectors, and that allow us to predict these oscillations. And our extractions matches perfectly what we observe. We can then, now we have to keep in mind that there has been a few recent studies that have pointed out that in certain systems, what be in other systems than iron, this may be a signature of double exchange behavior connected to the non-Heisenberg character. So we decided then to analyze this point more in detail, and we can do it here by applying a small strain to our system in a way to change the hopping parameter. So due to the scaling of the ferromagnetic double exchange and antiferromagnetic super exchange, we can actually expect two different scaling from this because we know it from theory side. And so if we do this analysis, we calculate all our contributions and then we fit them, we can obtain this number that I'm showing you here. And we can see that the D5 contribution is much, much larger than the D10 for all these, for these two curves that involves the EG electrons. So it means that the double exchange nature of the character of the EG electrons defines a very strong ferromagnetic double exchange components for the magnetism of iron. And now this can be is reflected by very different features in the Magnum spectrum. Now we can use this interatomic exchange to calculate the spectrum of the magnetic excitation, the spin wave spectrum. And this is what we can plot here, and we can see how different the T2G curve is from the EG curves, and how regular it is, and how irregular these are, and how irregular this is. So possibly our considerations can be probed in experiments. But most importantly, what we establish from this analysis is that iron is also an intrinsic antiferromagnetic component. Then what we can ask is, okay, but is there a way then that this antiferromagnetic coupling can emerge in iron if we do some shenanigans? And in fact, yes, this may emerge. In fact, there are a lot of results on concerning iron, for example, on thin films that show antiferromagnetic states. But then what we want to ask is that but then what we push in with this analysis is the fact that the antiferromagnetism is already there. So it's not driven by the hybridization. And this is in fact confirmed by our analysis of the surface of iron that you can see here. These are the plots of the interatomic exchange coupling obtained for a surface 001 of iron. And this J8 corresponds to the coupling of one atom in the bulk. So this is very similar to what I showed you before. You can see that you have this ferromagnetic exchange and then you have oscillations. Then the closer you go to the surface, then you see that things start changing. And then the surface, in fact, we get that the coupling in this type of coupling, the green curve, becomes antiferromagnetic. This is, in fact, the coupling that happens really among the atoms at the surface, while these other curves, they correspond, you know, to the coupling when you go down inside the bulk. So, and then we can see here that there are conditions that the antiferromagnetic coupling in iron can emerge even without changing the hybridization with a different substrate or with different, you know, expansion or general strain. Okay, so this is the end of my discussion on the transition metal elements, and I will now focus more on nickel oxide. As we discussed before, there are oxides where the 3D electrons that are rather itinerant in the transition metals, they may become more localized. Nickel oxide is one of them. Nickel oxide is in fact now categorized as a charge transfer insulator. But the basic picture that we can obtain in DMFT is, in fact, of a coexistence of MOT and charge insulating character, and I explain what I mean in a second. Let's start saying that the photoemission spectra of nickel oxide that corresponds to these dots that you see here allows to determine the presence of a large band gap of about 4 electron volts that you can see here. Now, if we do a standard DFT calculation for this, we will obtain something that has a very, very small vanishing band gap, or even no band gap at all, depending on the oxides and on the technique. And this is, of course, something wrong that does not represent the experimental picture. If we do DMFT, where we include the strong correlation of the 3D shell on a natural footing, then we see that the localized behavior of the nickel oxide 3D electrons emerges. This is what can be seen here. We can see that the 3D density of states plotted by this black curve, and we observe the presence of this multiplet-like structure that are a perfect match, almost a perfect match with the experiment. We also observe these high energy satellites that I think in experiment there, I don't know if these are, I think they correspond to this, yes, because this particular photoemission curve is done to maximize the 3D electron contribution. And also we observe this curve in the unoccupied part of the spectrum in this peak to be in a very good match. But also we observe that at the Fermi level, in fact, there is a coexistence of oxygen P states that are these red states, and of 3D states. So as a matter of fact, there is a sort of coexistence of MOT insulation and charge transfer insulation. But what I want to stress here is that we can, with DFT plus DMFT, we get a very natural account of this formation of multiplet-like structure in nickel oxide. And actually, the same thing holds for all transition metal monoxides. As you can see here, the agreement between DMFT data and photoemission data is in fact impressive. There are some discrepancies. For example, we can see it here in iron oxide, okay? You can see that there is this peak that does not appear in experiment. Does not appear in experiment. But we have to consider that iron oxide and cobalt oxide are a little bit difficult to synthesize. And the reason why is that it's difficult to keep the stoichiometry, in fact. So when you try, it's very difficult to have a pure iron oxide sample. Almost always you have clustering of iron 203, iron 304, this type of clustering. And these, of course, are going to change the spectrum because in theory, instead, we are just modeling a very simple, let's say, iron oxide ideal unit cell. But in fact, this actually is once you know that your theory works for the with a high accuracy for the ideal material, this can also be used to discriminate between different structure and maybe purity of samples and things like that. And so far I focus on the nickel 3D states, but as I mentioned before, we also should keep in mind that we always, as a theoretician, we should always strive to make our theory more and more accurate. So then one of the problems could be, okay, what does it happen for the oxygen 2p states, the ligand states? Are they well described in this approach or not? Because in principle, we are not treating them in DMFT. They are basically treated in DFT, so we can ask how accurate is this treatment. And this is something that we encounter in our study of the nickel oxide spectrum in collaboration with Professor Didi Sarma in India. As you can see, there is, by increasing the energy of the photon in photoemission experiment, this feature that we call tree increase drastically in weight. It becomes more and more dominant. So we can ask to what extent we can reproduce this in our theory. So for doing that, we mixed our DFT plus DMFT approach with a proper theory for the photoemission process, where we account of all the transition matrix elements and of the dependence on the photon energy. This you can see in these plots on the left. So if we look at the DMFT data that corresponds to this red curve for simplicity, we can see that as soon as we increase the photon energy, we get more or less that one of the features, this feature number 3, increases in weight. But also we see that it's located at rather the wrong position. Now, this is a nickel feature. I think it's due to the nickel, to some nickel states. I don't remember exactly the symmetry. But what is important here is that it is in the wrong position. And the reason why it is in the wrong position is because the extension of the oxygen 2p states does not come to be correct in DFT. And is not corrected by DMFT because DMFT is applied to the 3D states. And this is something, however, that has been investigated a lot in different type of semiconductor by another approach that is called GW, that is supposed to describe this effect. Because this extension of the oxygen 2p states is due to non-local effects, mainly, that are beyond DMFT. That's why we cannot even remedy in DMFT to this discrepancy, even if we want. And so then to verify this hypothesis, we merge our approach with the GW technique. As I told you, GW technique is another type of many-body theory that is done to investigate many-body effects in solids. It is a different approach than DMFT in the sense that it has some advantages, that it includes all effects, but also has some other disadvantages, like that is not able to treat very localized states. So it can only be used for moderate correlation effects. And when we do this merging, then we observe that the agreement now between theory and experiment becomes almost perfect, it becomes striking. We still have a little bit of underestimation of this feature, but I would say that better than this is very difficult to achieve, it's maybe even impossible to achieve in theory, because there are too many effects that are beyond all our approximations here. But we see now that the oxygen 2p states as the right breadth, the right width, and is also located in the correct position. Another nice thing we can investigate with DMFT for these systems is the X-ray absorption spectroscopy. This is another interesting probe that I will remind briefly to the students that maybe are not familiar with it. So this consists in shining the sample with some light, and then we promote transition for certain types of core levels to the unoccupied part of the spectrum. When we promote this transition, then we measure the number of absorbed photons with the detector. And this allows us to determine these absorption coefficients that then we can use to obtain information on the electronic structure of our materials. We perform this for nickel oxide, and you can see this because we have got a very satisfied description of photoemission, so we also expect a very good description of the X-ray absorption. And in fact, this is what we get. You can see the theory in black, and then you can see all these transitions from the core levels to the unoccupied part of the spectrum. And you can see that all the fine features, in fact, of the spectrum, they are described, this one, these two little one, this small one, these two, this other little satellite here. Okay, here I don't see, maybe it's a higher energy. So we really reproduce almost all features but this one, which is for a transition that is beyond our theory. Now, this is the importance of this. Let me tell you, so there are techniques that can investigate the X-ray absorption, but because usually they are techniques that they really require to include the atomic-like nature of the electrons in these transitions, because we are treating also the core states. And then usually this is done by multiplet ligand field theory. So which basically it's a theory that you do ad hoc for this type of experiment. The advantage instead of doing this directly in DMFT is that now we have everything. We have all our theory in the same machine, so in the same type of simulation. So we do not have to tweak anything because everything comes naturally out from these type of calculations. Okay, now I'm ready for the last part of my talk. Again, I tell you that if you have some questions that you want to ask on what we discussed so far, you are really encouraged to ask. And otherwise, I will continue and I will go on to the rare earth physics. Okay, I go on then. In the rare earth, now we are really in the localized realm of the electronic behavior, because the 4F states, they are very localized. These are the rare earth or lanthanide elements, so they go from lanthanum to lutetium, and they correspond to filling the 4F shell. So there are many of them. So, okay, as I mentioned before, we always have this competition between localization and delocalization. But in the 4F states of the rare earth, there is no competition, in the sense that the competition is won by localization big time. So the 4F states, they have their atomic-like character, and therefore they are inert. They are inert, they do not participate to the chemical bonding. What does it happen if we do DFT for this? If we do DFT, we obtain this yellow line. As you can see now, you have yellow states here at the Fermi level. This means now that your states are participating in the chemical bonding, because they really participate to the conduction and to the bonding. So it's not surprising that if your description of 4F states is so spectacularly wrong, that the final results are going to be completely wrong. And instead, when we do the DMFT that you can observe here in this green line, and we compare to the experimental spectra for the rare earth, then we can see how the spectra is perfectly reproduced by DMFT. In fact, the accuracy of all these multiplet structure is really striking, considering that here the parameters have not been tweaked to get a good match with the experiment. These are just the first parameters that we used. So if you optimize the parameter, you will get really each peak on top of each other, and with the experiment. And this is very natural in a sense, because in DMFT we are describing the atomic-like character exactly. So it's very natural that the more the electrons become atomic-like, the better we are describing them. So, and in fact, you can see here other type of elements like thulium, for example. You see this very complex multiplex structure, and you see that DMFT reproduces it rather well. We can also see it for praseodymium, for example. Actually, this allows us to describe another interesting thing. Here, I didn't explain you what is the difference between the green curve and the cyan curve. The cyan curve is the same as the green curve, is just that the spectra are normalized to keep into account of the energy background of the transition. So, and you see, in fact, that they account for all the discrepancy that there is between the DMFT density of states and the experimental curves. Actually, this allows us also to investigate another interesting feature, that is this formation of states close to the Fermi level that appears for praseodymium, because some people in the past, they had hypothesized that this may be some sign of Kondo-like resonance or some very sophisticated many-body effects. But in fact, with our data, we show without a doubt that these states are really due to the D states, so to the 5D states that appear around the Fermi level. And when you keep the background into account, they can describe the presence or absence of this feature close to the Fermi level for all rare earth elements. You can also simulate the cohesive properties, and this is what we observe. You can see the experimental volume as a function of the rare earth type given by these red dots, and you can see here these features. You can see that there are some elements have almost constant equilibrium volume, and this is because the 4F states are inert, so they don't participate to the bonding. So the more you add, it doesn't matter for the bonding. Still, you see some differences. They decrease, the volume decreases a little bit. This is called Lanthanide Contraction, and this is due to incomplete screening, because as soon as you are adding one more proton and one more electron to the system, the electron cloud doesn't screen the proton, the additional proton exactly, and so this shrinks the system a little bit. And you can see also that there are three elements that have a much larger volume, and this is due to the fact that these elements, they are divalent, so they have only 2 SPD binding electrons, while these other ones, they have 3. And this is due to the fact that the stability of europium and ytterbium is very close to the half-filled shell, so they prefer to get a half-filled 4F shell and then to have 1 less electron in the SPD band. But we can see actually that the DMFT data that corresponds to this green curve is really on top of the experimental points with very, very good accuracy for all elements, but maybe we get some discrepancy here for these elements, but it's almost on top. And okay, then we can also analyze the structural stability, and we use praseodymium and neodymium as a test case, and also in this case we analyze different crystal structure and we find the right one. So for example, for praseodymium and neodymium, we find that the HCP phase is the most stable of all. We can extend this and also evaluate the bulk modulus, but I will not focus on this. You can see that the agreement for the bulk modulus between theory and experiment worsens a bit, but this is normal because it's not so easy in theory to get it accurate. Then I want to focus a bit more on the magnetism in the rare earth. And we can observe, we calculate the inter-atomic exchange coupling again, now for the lanthanide, for the rare earth elements. And we observe this trend. Again, we observe high distance oscillation of RKKY type. In fact, the rare earth elements, they are really standard elements to describe this RKKY coupling. We can see also how the coupling decreases going from gadolinium to thulium, which is consistent with the decrease of the magnetic moment across the series. Consider that gadolinium is half-filled, so it's a very sharp, strong moment, and then the more we fill the 4F shell, the more we decrease this moment. Okay, it's not really so linear because there is orbital moment as well, but let's say in general, we are decreasing the moment in this direction. And we can use actually this inter-atomic exchange coupling to perform multi-scale calculations of the Heisenberg model to be solved then via Monte Carlo method. And we can obtain in this way the ordering temperature of the magnetism. And again, we can see how in good agreement is this with experiment. So we can predict the evolution, the decrease of this ordering temperature from the high ordering temperature of gadolinium to the small ordering temperature of thulium. Another thing we may be interested, in fact, to reproduce is the instability of towards a spin wave formation. Because in rare earth elements, the magnetism is very complex. When you go to lower and lower temperature, some of these elements, they start developing very complicated helical spin structures. And it is in fact very difficult to stabilize a ferromagnetic state, for example, in erbium, because you should really apply crazy magnetic field. And in principle, we should be able to see these from our interatomic exchange coupling. So, and if we perform a Fourier transform of those using the adiabatic approximation, we can now plot these quantities that are the Fourier transform minus the value of the gamma point. And the highest state should give us the minimal energy state. And as you can see in the zoom in that we show in the inset, there are two elements that have a maximum that is not exactly at 0. So it does not correspond to a ferromagnetic state, but it corresponds instead to a more complicated spin structure. These two elements are in fact erbium and thulium. And this is good because erbium and thulium, in fact, in experiment, they are reported to have this spin, helical spin state. Holmium, however, is also reported in literature to have an helical spin state and is not now described by our theory. Why? Recently, we actually completed an implementation of the anisotropic effect on the exchange. So now we are including additional terms then to this isotropic exchange coupling. And these allow us to understand what effects what these anisotropic terms lead to. For example, a very famous anisotropic effect is the Januszewski-Moria coupling. So we calculated these things, and in fact, what we find is that for holmium, including these anisotropic effects leads to a reduction of the first neighbor coupling. So this reduction, it means that in fact, in our previous analysis, we probably overestimated the weight of the ferromagnetic order. So most likely, we are now repeating this analysis for holmium using this new data, and we are very confident we will obtain the formation of a spin spiral also for holmium. Another thing that this can be used for is the analysis of the Magnum spectrum. So now we can again calculate the magnetic excitation. We did it here for gadolinium. And what we can observe is that the agreement between experiment and theory is really striking. Again, this should not come as a surprise that the rare earth elements, they offer a very good agreement with DMFT, because the atomic physics in this method is supposed to be described to a very high accuracy. So, okay, so that's depending on the time, because I see that if we exclude the first minute, I talk for about 50 minutes. So I have a last part that I could present, or I can stop here. So I ask the chairman, Professor Battiato, to tell me if I have still 10 more minutes to go through this, or if we want to stop here.
Igor, if you want, I guess you can go ahead.
Okay.
I mean,
okay, because this offers a nice twist. So I would like to present this because I think it's very interesting result. Because so far I presented to you the analysis of the magnetism that is based on the inter-atomic exchange coupling that you can see is depicted here on the left. So we are calculating the coupling between magnetic moments sitting at different ions. But as a matter of fact, in rare earth elements, there is another coupling that is very important, and it is intra-atomic exchange coupling. So in particular for rare earth, this is, for example, the coupling between 4F and 5Ds at the same site, because if you exclude this coupling, actually the 4F elements, they do not hybridize with each other, the 4F electrons. So there is no way that this magnetic moment could actually communicate with this other magnetic moment. But in fact, they do it through the 5D electrons, to the SPD electron band in general. So then the strength of the magnetism is strongly defined. Oh, sorry, is strongly defined by these 4F to 5D coupling. Now there is in the past there has been no direct experimental access to the intra-atomic exchange, and this is due to a bunch of competing effects. So, for example, it becomes very difficult to distinguish for the inter-atomic exchange, the one on the left, but also from crystal field effect and also from spin-orbit coupling. So really disentangle all these effects with a generic technique like photoemission is, for example, very difficult. So, and here I hope that I can convince you that we report on the first experimental, first direct probe of the intra-atomic exchange. So our experimental colleagues perform experiment on the rare earth adatoms deposited on graphene, which is in turn deposited on iridium or copper. And you can see a scheme of what they measure by means of inelastic electron tunneling spectroscopy that I will call YITS. In YITS, the tunneling electron, I don't know, probably this name has a different pronunciation in English, I really apologize, but I never heard an English speaker pronounce it, so I have no idea. So the tunneling electron can exchange momentum with localized spin. This usually is used to study vibrations, for example, because then when you can exchange this momentum with a certain type of excitations, then you will have steps in the conductance curve, so the DI over dB curve that you can measure. So this is the results of the measurements. You can see they investigated adatoms going from lanthanum to ytterbium. And you can see several features here. you can see that some elements, they show a very flat profile, like lanthanum and ytterbium, for example. Some other elements, they show, for example, two steps symmetrical, let's say, the presence of one step, and like europium. And most of the elements instead, they show the presence of two steps. So one at a larger energy scale and the other one at a smaller energy scale. What is the origin of this step? This has been a very interesting question for us. Let's analyze some of the possible causes. Maybe we can assume that we are measuring crystal field level transitions in the ground state multiplet, okay? So for multiplet, what I mean is what I showed you before, just to make it clear. Okay, this was maybe too optimistic in going fast back. So for multiplet, I mean, for example, this, okay, all the presence of all these peaks corresponding to all these different states. I hope that you remember this from the atomic physics. Okay, now I have to jump back. Okay, there is a problem, however. These crystal field transition, they are too small. The energy scale doesn't match what corresponds here, which is of the order of about 0.1 eV. Maybe these correspond, in fact, to the small conduction steps that we can see here. Maybe these are really the crystal field things. Maybe we can assume that these are excitation to the first excited state multiplet, so from the ground state to the first excited state multiplet. However, these are the opposite problem, that if you remember the previous energy scale, I will show you that these peaks, they are distant, they are on the scale of the EV, so they are too big for what they measure here. And also should appear for all elements, so there is no reason why, for example, ytterbium shouldn't show them. Or also terbium, that I'm not reporting in this figure, doesn't show any of this. Maybe we can also assume that this atomic vibration, because this heat is used to probe atomic vibration. But then in this case, this behavior should be really monotonic, and it should depend on the atomic mass, as a matter of fact, and should appear for all elements. So none of these possible explanations matches the experimental observation. So in fact, we are really convinced that we are measuring, we are giving a measurement of the intra-atomic exchange coupling. To model this, let's consider what happens for a rare earth atom in the gas phase. We have this electronic configuration with, for example, with 4f electrons in an n for 4f electrons, and a fully filled 6s shell. For example, for this prosium, we are going to have this configuration, where the 4f states, they order accordingly to one's roles. And what does it happen when we deposit this atom on graphene? Now there is a strong charge transfer due to the formation of this bonding with the p states of carbon. And therefore, about one electron gets transferred from the rare earth impurity to the graphene. As a result, now we have one less electron, so we have a partially filled S shell. In reality, it's a bit more complicated because you have the formation of an SPD-like band, so you cannot really distinguish so easy. But let's assume for a moment that we have simply one 4s electron. Then, when we are probing now with yields this material, the yield selection rule will in fact induce a flip of this 6s moment from this configuration to this configuration. Now we have this different arrangement between between the 4f moment and the SPD band moment, and this is in fact exactly the measure of the intra-atomic exchange. If this is correct, then the energy of this process could be modeled by this Hamiltonian, where we have the 4f, the intra-atomic exchange coupling, times the moment, the magnetic moment of the SD band, times the magnetic moment of the 4f shell. If we assume, in a very simplified model, a constant filling of the of the SD shell that corresponds just to one electron, so really half-filled shell, then we are going to have an occupation of 1/2, and then we can fill all the data here in this expression using tabulated data from literature. And we get, in fact, that the experimental points that correspond to these colored points are a rather good match to the simplified model. But in fact, we can also do a more, now here, just to keep in mind, we are plotting this energy of these steps here, okay? So this energy, EX, of these large steps. So, okay, my computer is a bit slow. Okay. We can, however, formulate a more accurate model by using DFT or DMFT. These data are for DFT, but we can also do it in DMFT. And we can actually analyze all different issues related to this problem. First of all, we see that the element we calculate now that corresponds to these crosses are in perfect agreement for the later Earth, and are in good reasonable agreement for these two. It's a bit overestimated, but there are a lot of approximations in our theory. We have to consider. And this offers a more realistic description, because now we are not assuming any moment, we are calculating them exactly, exactly, at the best of our ability. And the magnetic moments now that involve also all the electronic shell. We are also calculating now the intra-atomic exchange coupling from scratch, which is again something not simple. So the expression we use at the end involves all this contribution. This offers a good quantitative agreement, but is also explained now the absence of the step for lanthanum, terbium, and deuterium. So lanthanum, it will not have. For the elements that, for example, like terbium, they get in a divalent configuration. In a trivalent configuration. This means that now we have one more SPD electron in this shell. So this means that the energy of this excitation is going to be much, much larger than what we are measuring for these elements. So as a matter of fact, also this terbium should show the same steps, but just they are outside the experimental range. So we can also discuss on what leads to the observed discrepancy. That can be, the better analysis of the substrate. We analyze the crystal field effects in the DMFT, and we find that they only lead to a very small correction, so it cannot be crystal field what creates these problems. My guess is that the anisotropic terms, they have an important role. So the anisotropic term of the intra-atomic exchange that they have never been studied in literature, or they've studied by some approximate method maybe in the 70s. So, and now actually we are working on trying to implement this and to figure out if we can explain the remaining difference between theory and experiment. Okay, so this was all. I hope that I provided you with a good overview of all these systems with strong correlations. And I thank you very much for your time.
Okay, Igor, thank you very much. Fantastic results. Okay, so let's see, are there questions? Okay, maybe Igor, I have a question. So it was regarding the very beginning. So when you were showing, I think it was nickel, and you were showing how DMFT can reproduce the reduced bandwidth in comparing to I think the next slide or the slide after that. So you were showing ARPES, this one. So you were showing experimental ARPES. So so what they were seeing. But one second. So first of all, why? So I suppose that the dots are experimental results.
Yes.
Why are there only dots and not like full ARPES?
We have the full ARPES, but then it's a bit tricky to compare. That's why.
Okay, so you're extracting just.
Yes, we are extracting because it's easier to compare. But if we look at the full ARPES, you can see it here, for example. This is why I was showing this. So this is the gamma point for iron.
Yeah, but
And
this
you can see,
this is integrated over.
no, I think this is the gamma point.
This is only gamma. Ah, okay, okay.
This is only gamma projected on the surface. So as you can see, so this is normal emission. Okay. So as you can see here, the experimental curve is this one. And if you really want to get these curves correctly, you should, you can see on the right side that you should use a rather large U, like U equal 3V. But the problem is that if you do that in iron, then you have problems in describing this peak. And the reason is because the correlation is non-local in iron. It has a tendency to have these non-local correlations.
Okay, so my question, so if you go back to the ARPES dots.
Yes.
So I see, for example, in the, so in the majority channel, it seems like you can catch most of, like very well, all the bands close to the Fermi level.
Yes.
In the minority channel, so I see around, like, let's say, closer to the A point. So there are minority states very close to the Fermi level.
Oh, you mean these? But these are surface states.
Ah, okay, okay, okay. Yeah, because then I was like, wow, that's a big difference. So if you miss, okay, so those are surface states. Okay, I see, I see. So then
at least this is what the experimentalist, that is Jaime, claims.
Okay, okay, okay. I see, I see. Oh, but in principle, so this is for HCP Cobalt.
Yes.
So okay, so do you mean that already for HCP Cobalt, the, how to say, like a relatively precise experimental band structure is not fully known yet?
I mean, you have to decide what you mean for precise experimental, because you know, somebody, what you are interested in. So because I think that the aim of these studies is more to understand what is, you know, the real electronic structure in the bulk, because this is
definitely.
This is what you are going to exploit. So if there is some surface state, in a sense, I don't want to say that you don't care. You care, but you care if you are doing surface science. So,
no, definitely. That's why I'm asking. Because let's say state that close to the Fermi level starts having important effects.
Yes, yes, I agree. But this, you know, you can determine this in the analysis of the symmetries. When you take different polarizations, then you can analyze the symmetry of the states. You can see if they disappear or they remain there. You can do different things.
Okay, okay, I see, I see, I see.
And
okay.
You can see how dispersive they are. You know, you can really identify what is what. And in reality, if you go to compare with very accurate ARPES measurements, then it's always very tricky, because you will always have a bunch of states and resonances. So, and the same, for example, holds for the comparison you have here on the right side for the lifetime. You know, you may, if you look at this curve, you may say, okay, but you tell me that, for example, you are you have a good agreement of the lifetime, but if we look well, they disagree of 50% between theory and experiment. And this is true, but you have to consider also the fact that in the theory, there are many effects are lacking that contribute to the lifetime, like, for example, the scattering with defects or the scattering with phonons. I mean, there is really a lot of effects that enter into the calculation of a real material. And,
okay, sure. So what you're showing there are actually scattering rates. So that's the, so not like, okay, okay. So you're definitely underestimating the scattering.
Yes, we are definitely underestimating.
Yeah, okay, okay. That makes sense, because if you were overestimating, that would be definitely a problem.
No, that would be yes, that would be absolutely a problem. And
okay, okay. Okay, any other question?
Oh, okay. So thank you for your talk. Yeah, on this technique. So I was wondering if you have tried this technique on transition metal alloys. So for example, like iron, platinum.
That's a very good question. So I tried it a lot on impurities, or if you want to say in doped system, but in the dilute limit. And there are studies where they investigate this. In fact, I think there is a study on iron platinum by Jan Minar in the group of Professor Hubert Ebert. So no, I didn't focus on this type of alloy, but more on impurity. So for example, on manganese doped gallium arsenide, and now I'm working on doped topological insulators. But in principle, yes, you can couple it also for doing alloys. It's just that if you do alloys, so the main problem is technical here, okay? So if you want to do alloys, like for example of if you want to do alloys in this formalism, you have to do it with that I'm using. You have to do it with a supercell approach. And if you are doing now a supercell of DMFT, that can very easily hit your computational limit very fast, unless you work in the dilute limit, as I told you, and then you can consider just one impurity, you know, in a supercell. However, in the group of Professor Hubert Ebert and Jan Minar, they were doing that because they have a DMFT code which is based on KKR method, on Green's function theorem. And then it's much easier because then you can do the alloy theory by means of CPA, coherent potential approximation. So, and if you do it in that, then you can merge CPA and DMFT and try, you know, to model these systems without having to wait for, let's say, years before your results converge.
Okay, thank you so much.
Thank you.
Okay, any more questions? Okay, well, I guess we are already over time. So let's thank the speaker again. So Igor, thank you very much for giving this talk. And anyway, so well, I guess you can if you have questions, if you're interested in Igor's work, I guess it's easy to find him. And in case, you can always write me, and I will put you in contact with him. And okay, so, and yeah, I guess that's all. We can close the session here.